Hi, this is Fabien Horer from Cyberbotics. I want to show you in this movie how we can interface Matlab and Cyberbotics Webots. And the aim of this movie is not about how to install them. I have done this screencast on Mac OS X, but this is not necessary to use Mac. Windows and Linux are working almost the same once Webots and Matlab are installed. The documentation about installation can be found in our user guide in installing Webots section and in the language setup section here. So I expect Matlab can be run and can be used. It seems to work. Okay, I can quit Matlab. Secondly, Webots is also installed and is running. The first thing I want to show you is where I can find MATLAB sample. So in the Webots directory, you can go in Projects, Languages, MATLAB, Worlds, and Epoch MATLAB. So maybe I will start by showing the example and the Webots interface. So as usual, we have the 3D view there. We can see an Epoch robot there. The definition of the simulation can be seen in the scene tree representation there. We find, for example, the Epoch node there. And here we have the MATLAB controller. When I run the simulation, the result of there is a collision avoidance algorithm, and the result of the cameras of the Epoch is shown there, and we have several other information. It's interesting to look at this code to see how it is done. But the main aim of this screencast is about to create a new project, a new MATLAB project, and this can be done. First, I always stop the simulation before starting to modelize something. It's much more convenient. So we have a bunch of wizards there, including the new project directory. New project creation. I can continue and select a directory. Here I put it directly on my desktop. My first MATLAB simulation. Open. And Webots create a bunch of subdirectories. which are the standard directories used by Webots. Here it's the simulation file, which will contain all the nodes and the robot definition and so on. And the other interesting thing is the controllers directory, which will contain the MATLAB controller. Okay, so a new project is started. We are now there. I can close that because it's the previous sample files I showed you before. And here I can obviously add new objects, new obstacles, changing, for example, the rectangle arena size. And I want to add a new robot from Webots, from the robots library of Webots. It's the epoch because it's quite simple, only a differential wheels with distance sensors, a camera, and so on. So here's the epoch. Here is the epoch. I change the viewpoint in order to see what's going on. Okay. Next step. I can already save the simulation here because I changed several things, including the rectangle arena size. I added an epoch and I changed the viewpoint. I can now add a new robot controller, MATLAB, my first MATLAB controller, continue. As said before, it is put in the project directory I created before and in the standard controllers directory. Okay, here is the MATLAB controller. So, next step is about to link the epoch robot with this controller, and this can be done with the controller field of the epoch node. And normally I found the controller I just created in the list of controller. Can save again. Now just take a look at the structure of the controller. We have a main loop. Each loop is stepped by this function, WBRobotStep, which will perform a physics step in the simulation. So after this main loop, we can define new things, initialization stuff, for example. And after the loop, we can clean up the code, save some data typically. So the first thing I want to do is to let the robot go forward. I know that the epoch is a differential wheel node because when I look at its definition, it's a differential wheels node. So I can access to all the differential wheels functions in the controller. Okay. When I look at the differential wheels node in the documentation, I will have the list of functions available. I can just show you that. If I go in the reference manual and select other APIs and then Matlab APIs, if I look at the differential wheels node, I have the list and the list of functions I can use, including here WB differential wheels set speed. This function will allow the user to specify the speed for the differential wheel robot. And there is a more detailed explanation. Okay, so if I know that the range of the speed of the robot are between minus 1000 and 1000. The aim of this screencast is not to tell you how these values are defined, but just a word about that. It's about the definition of the epoch photo there. So if I just put 500 and 500, the robot will go forward if I revert and play the simulation. Of course, there is no collision avoidance algorithm, so the robot hit the wall. Okay. Next step is to get the sensors. I know that the sensors I want to use is PSO and PS7. This one and this one, it's the two front distance sensors of the epoch robot. The definition can be found also in the photo file. If I look at the name of the distance sensor, I see their IDs match the pattern PSX, where X is the ID of the distance sensor. So I can get PSO by getting the device from the robot and using the corresponding ID, and PS7. Here is an object matching with the sensor. Then I have to enable it. The enable function take first the object argument, and then at which rate the sensor updates will be operating. And finally, I can just get the values of the distance sensor at each step. Get value PSO, and that's it. So now at each step I get the distance sensor values. Next step is to do some computation with them. Just doing a delta, a difference between these two values will allow me to do a very simple collision detection algorithm. And I want to set the speed of the robot. Oh, I just lose the epoch view there. Okay, and here I can let it go forward and adapt the differential wheels according to the distance sensor values. I'm lucky there because these values are matching very well, because the range of the distance sensor is at the same order of magnitude of the differential wheels speeds. But I don't want to enter in the details there. The aim of this screencast is about speaking about the API and the nodes and the relation with the Matlab controller. Okay, so now I think I have a collision avoidance algorithm. So what's going on? The epoch distance sensor have a small noise. So the epoch is rotating a little bit, and when approaching to the wall, the epoch turned. It's not perfect, obviously, but the idea is shown. Next step is about to have a more complex sensor, which is the camera. The camera has to be enabled to get enable, and exactly as the distance sensor, we can just get the camera values, the camera image in a three-dimensional array using the camera get image function. What is interesting here is that we can use the MATLAB plotting abilities to see this image at each step and doing small operation on the RGB values. For example, I can the draw now function here line is about to flush all the plotting information to MATLAB. So just before that, I can use all the standard plot function of MATLAB, plot, subplot, and so on. And here I'm interested in using the image function of MATLAB, which will display the three-dimensional array of the camera sensor to and plot it to a MATLAB figure. So just by adding this line here, you should be able to see the camera in MATLAB. Just play it, and here we are. MATLAB is plotting the camera here. So you can think about plotting whatever function or stuff in MATLAB using this way. Okay, thank you a lot for watching this movie. and I hope you enjoy it. Thank you, bye.